Hello everyone. Today we will talk about our project. Our project is a replication. The paper we picked is towards deep learning models resistance to adversarial attacks. This paper looks at models of different levels of adversarial training and evaluate the robustness of three models towards three different data. So our experiment is implementing FGSM PGD algorithm, training three defense models. Except that our new experiment also add another adversarial attack, IFGSM. We will use this method generating data as another test data for each models. And we add this method training model as the third model. We will compare these three models and see which defense method is the most robust to the test data. In a word, there are three defense methods we will compare. Before we talk about our project, we will tell you the structure of this project. First, we will introduce the background. Then we will talk about optimization view on adversarial robustness. The third is three attack methods. The fourth is our experiments. And the fifth is our conclusion. First, let's talk about the background. Uh, As we all know, deep neural network is very impressive in a variety of fields. With the computing power improved and tools improved, a series of machine learning models began to achieve amazing performance on different machine learning tasks. So far, anyone would be surprised if machine learning algorithms didn't do the right things. However, the phenomenon of misclassification of neural networks still appears. Computer vision faces big challenge. Making small changes to the input image can fool the most advanced neural network. This is true even if the benign example is correctly classified and the change is imperceptible to humans. Therefore, this phenomenon shows that our current models are not learning the basic concepts in a robust way. So how can we train a model which has a good robustness to the adversarial attack? It's an important question for us. First, we need an optimization view on adversarial robustness. Uh, in order to solve the question mentioned above, we need a guarantee that adversarial robust model should satisfy. Then we adapt our training methods towards achieving this guarantee, and we can see that guarantee is shown here. This formulation gives us a unifying perspective. In this perspective, problems have a natural interpretation in the context. The inner maximization problem aims to find an adversarial version of a given data point x that achieves a high loss. This is precisely the problem of attacking a given neural network. On the other hand, the goal of the outer minimization problem is to find model parameters so that the adversarial loss given by the inner attack model is minimized. This is precisely the problem of training a robust classifier using adversarial training techniques. So our experiment just did like what's said above. Attack a given neural network and train a robust classifier using the adversarial data. So how do we attack the neural network? We have three methods. First, FGSM. On the attack side, prior work has proposed methods like the FGSM and multiple variations of it. For example, IFGSM we used. We will introduce FGSM. FGSM is an attack for L infinity bounded adversary and computes an adversarial example like this. We can interpret this attack as a simple one-step schema. which maximize the inner part of the saddle point formulation. And another method, a more powerful adversary, is the multiple step variant, which is essentially PGD on the negative loss function here. So there are many other methods like FGSM with random perturbation, but we don't use them here. Clearly, all of these approaches can be viewed as specific attempts to solve the inner maximization problem. On the defense side, the training data set is often augmented with adversarial example produced by FGSM, IFGSM, and PGD. To solve the simplified robust optimization problem, we replace every training example with FGSM attack data, IFGSM data, and PGD data. More sophisticated defense mechanisms such as training against multiple adversaries can be seen as a better, more exhaustive approximation of the inner maximization problem. So what is the difference between this method? As we point above, linearization, the inner maximization problem, use very well-known methods such as FGSM, while training against FGSM adversaries has shown some success. Recent work also highlights the important shortcomings of this one-step approach. Slightly more sophisticated adversaries can still find points of high loss. To understand the inner problem in more detail, we investigate the landscape of local maxima for multiple models on different datasets. The main tool in our experiments is a projected gradient descent. We restart PGD from many points. Surprisingly, our experiments show that the inner problem is tractable after all, at least from the perspective of first-order methods. While there are many local maxima spread widely apart, they tend to have very well concentrated loss values. Our experiments show that the local maxima found by PGD all have similar loss values, both for normally trained networks and adversarial trained networks. This concentration phenomenon suggests that the PGD adversary yields robustness against all first-order adversaries. So we think PGD training model is the best defense model among all first-order approaches. So next, let's see our experiment. Let's check whether PGD is the best defense strategy. So first, we can see that this shows the model trained with natural examples. We can see that it predict if it predict the natural data, its accuracy is very high, but it is not robust to other attacked data. It's very low, right? 20%. And then we can see the model trained with FGSM examples. We can see it is good for natural data, and FGSM data is good good too, right? Not bad, 60%. But it is very bad to FGSM data, and PGD data is 0%. And we can see the model trained with IFGSM examples. We can see this is a lot better than the two models before. It is good for natural data. Also, it is good for FGSM data, 80%. And it is not bad for IFGSM data and PGD data. It is better than the two models before, right? but it is not the best. The best is the model trained with PGD examples. We can see it is also good for natural data and FGSM data, right? But it is a little lower than this one. But it is very good for FGSM data and PGD data compared to all other models. Let's see the average accuracy performance for these four models. We can see PGD, the accuracy of PGD model is the highest, and then RFGSM, and then FGSM, and the last one is natural. We can see the accuracy of PGD model can achieve 80%. So we will talk about our conclusion. First, our findings provide evidence that deep neural network can be made resistant to adversarial attacks, as our theory and experiments indicate. We can design reliable adversary training methods. One of the key insights behind this is the unexpectedly regular structure of the underlying optimization task. Even though the relevant problem corresponds to the maximization of a highly non-concave function with many distinct local maxima, their values are highly concentrated. Second, among all the attacks, PGD defense model has the best performance. So this is our project. Thanks for watching. Bye.